Let us now discuss the Sommerfeld theory of conduction in metals. So this is basically the application of Fermi-Dirac statistics to the standard properties that we discussed in the Drude model, DC conduction, specific heat, which we already did, thermal conductivity, thermopower, and so on. So this is a schematic of the Fermi sphere, of course drawn in two dimensions at t equal to 0 and at time t equal to 0, that is before the application of an electric field. And in the absence of an electric field, you can see here that the Fermi sphere is centered about k equal to 0. Remember that k is related to the momentum, and you can see the momentum in the positive the positive quadrant cancels off the momentum here, the momentum here cancels off the momentum there, and so on. So the sphere is stable and stationary. When you apply an electric field which results in a force, let's say in that direction, then the electrons, all the electrons will experience a momentum, or it will be a shift in the wave vector delta k, and because of this the Fermi sphere gets displaced like that as shown. Of course, this is a very schematic depiction. So this force can be written as h cross del k by t, where del k is a shift in the Fermi sphere, and the momentum also is related to this velocity, this v equal to h cross del k by m, and that of course is also related to the force in this manner, which we saw in the Drude model. And you can take the expression for the current density, which we looked at earlier, and replace this expression for the force, and you get back the Ohm's law. So nothing changes with respect to DC conduction, because although there is this idea of the shift in the Fermi sphere, but this is basically equal to the standard force that you can write in the classical model as well. So nothing changes with respect to the DC electrical conductivity, and you get back the Ohm's law. The only difference is now when you want to calculate the mean free path as the velocity times the relaxation time, instead of just the classical velocity, you will now put in the Fermi velocity, because the conduction occurs because of electrons at the Fermi surface. So you have Vf times tau, and this comes to about 100 angstroms, whereas in the classical case you got about 1 to 10 angstroms. Here you get about 100 angstroms. This is more in agreement with the experiment than the classical model. And also if you consider a temperature dependent model of electrical resistance, you can see that the mean free path becomes longer at lower temperatures. Now coming to the thermal conductivity, we saw that the expression for thermal conductivity is basically this: 1/3 the velocity squared times the relaxation time into the specific heat. And if you look at the classical expression for V squared, this is of the order of kT. That's just the equipartition theorem. But if you consider the Fermi-Dirac expression for V squared, this is of the order of EF, and this is of the order of the Fermi level. So you can write that the classical expression V squared is proportional to the Fermi-Dirac expression for V squared times kBT by EF. So that is, the classical expression is 1 by EF times lower than the Fermi-Dirac case. That is, we saw that in the Fermi-Dirac distribution, the electrons at the Fermi level have very high velocities compared to the classical case. So that is why the classical expression for V squared is 1 by EF times lower than the Fermi-Dirac expression. On the other hand, if you consider the specific heats, I can now write that the Fermi-Dirac expression for the specific heat is proportional to the classical expression for the specific heat times kBT by F. That is, the classical expression for the specific heat is very high, and the Fermi-Dirac expression for the specific heat is 1 by EF times lower. So I can now combine these two, and I can now write that classical expression for the velocity is proportional to the Fermi-Dirac expression for the velocity into kBT by F. And I can also write the classical expression for the specific heat is proportional to the Fermi-Dirac expression for the specific heat into EF by kBT. So that's the inverse of what I just wrote here. And so if I now multiply CV classical into V squared classical, I will basically get CV order of magnitude, I will basically get the same number as CV Fermi-Dirac into V squared Fermi-Dirac. The reason I'm doing that is because the thermal conductivity has got a V squared into CV in the expression. But whether I use classical or quantum mechanics or the Fermi-Dirac, the product of CV into V squared will be the same, and therefore the expression for the thermal conductivity does not change much. Of course, the relaxation time changes by a factor of 10, but the V squared CV time term does not change much. And as we saw in the expression for the Wiedemann-Franz law, the Wiedemann-Franz law is basically the ratio of the thermal conductivity to electrical conductivity, and it says that it's proportional to the temperature. So if I take K by sigma, then the relaxation time, which is the only factor that differentiate classical physics and quantum physics, that drops out. If I take K by sigma, the tau goes away. So K by sigma t classical expression is this, and the quantum expression is for K by sigma t is this. Aside from this factor, the numerical factors, the kV by E whole square term is reproduced exactly. So the Drude model, that is why I kept saying that the Drude model was an accidental victory with respect to the Wiedemann-Franz law, because the Drude model overestimated the specific heat but also underestimated the velocity by the same factor. So if I take the product, the mistakes vanish, and therefore you kind of stumbled upon the right answer. Excuse me. So it's accidental, but it's a very remarkable similarity between classical and quantum models that tell you that this approximately is correct. Finally, you have the thermopower. We saw the expression for the thermopower as this. Now we just saw that the classical expression for specific heat is proportional to the Fermi-Dirac expression times EF by kT. So I would like you to plug that in and find out the Fermi-Dirac expression for the thermopower, and obviously the thermopower would be about 100 times lower, because the classical value is an overestimate. Therefore, the thermopower estimated by the Drude model will also be 100 times more. In the Fermi-Dirac case, it will be 100 times less, and that matches with experiment slightly better. So we'll continue talking about the limitations of our model. Even with the application of quantum mechanics, there are still some limitations. We'll consider that and see what to do about it in the future classes.